Hello and welcome to Engineering Safari. And today we'll be covering one of the most fundamental topics of communication engineering, which is continuous and discrete time signals. So, this is a completely mathematical topic. There's very little to no theory. So, we'll just brush up the main concepts as fast as we can and practice a few questions per topic. So, with that, let me just give you an introduction to all the topics that we'll be learning today. So, to start off, like I mentioned, this is a topic which is purely mathematical. So, it's very essential that anyone who's studying this module has the basics of trigonometry and integration right. So, to start off with this video, I'll be briefing you about the essential trigonometric formulae which will be needed further in this chapter, as well as how we can integrate as fast and as efficiently as we can. And following that will be an introduction to signals and systems, like what is a signal and what does a system do. And then we'll be talking, in this module, we'll only be talking about signals. We'll talk more about systems in the upcoming module. So the first thing about signals that we'll learn is the basic categories that exist of signals, which are continuous and discrete time signals. And then we learn how signals are represented in graphs and how, if a signal is represented in a graph, we write the mathematical form of it. Then we learn how multiple operations like addition, subtraction, and multiplication can be performed when two different signals are given. Then we'll learn about amplitude scaling, time scaling, and other variable transformations that are done on a particular signal. After that, we learn about particular important significant signals which are always used in questions like unit step, delta function, and unit ramp function. And after that, we'll talk about further classifications of signals in which we have even, odd, energy, power, and periodic and non-periodic functions. After that, we have orthogonality, orthonormality, and what are the conditions for a signal, for certain signals to be orthogonal or orthonormal. And then we talk about mean square error, which helps us to represent one signal in terms of another signal. And then we have a few very minor topics, which are norms, moments, and linear dependency of vectors. And we are not going to solve questions for this at the end of the module because, like I said, it's almost fully mathematical. So we'll be solving questions after each topic. Okay, so to get us started with, we'll discuss the basic mathematical tools which are essential for us in this module. So these are the trigonometric formulae that are essential. We don't need to derive any of them. You just need to, unfortunately, you have to memorize all of this. So just take a screenshot and memorize all of these. These are the only formulae that will be essential. You don't have to go too much in depth either. And then we'll be talking about integration by parts. So if you are integrating a product of two functions, let us say u dot v, how does this integration happen? This is done using integration by parts, and I'm sure most of you are familiar with the long formula that has been taught in class 12. But since that is not, we don't have to show the steps for that here. I'm going to tell you a much easier method using which integration is much easier. There is less scope for mistakes and it happens faster. So the first thing that you have to do when you're given a when you're asked to perform an integration of a product of two functions is you have to choose u and v. So the order for that is uh, called the Eilert preference order. So here I stands for inverse trigonometric functions, L stands for logarithmic functions, A stands for algebraic functions, T stands for trigonometric functions, and E stands for the exponential functions. So if you have two functions, let's say x square into e to the power x. So x square is an algebraic function and e to the power x is an exponential function. So our first preference will be given to x square. So x square is b, x square is u and e to the power x is b. Similarly, if we have x into cos x. So again, x is an algebraic function and cos x is a trigonometric function. So we take x to be u and cos x to be v. So now let's talk about how the integration is actually done. So now that we have selected u and v, what we do is we write uh, di and write u under d followed by v under I. So what we do is we go on differentiating u until we get 0. And the number of times that we have differentiated u, we integrate v the same number of times. And then we add alternating plus and minus symbols. This is plus, minus, and plus. So after we add the alternating plus minus symbols, we go on multiplying the first term in D with the second term in I, and then the second term in D with the third term in I, and we add all of these products. So for an example of this, let's say we have integration of x square cos x. So here x square is an algebraic term, so it's taken as u, while cos 2x being the trigonometric term is taken as b. So we write x square under the d column. Differentiation of x square gives me 2x. Differentiation of 2x gives me 2. And differentiation of 2 gives me 0 finally. So I do not have to proceed with this any further. So since we have we had to differentiate it 4 times to get to 0, we'll integrate cos 2x 4 times. So integration of cos 2x gives me sine 2x by 2. And integration of sine 2x by 2 gives me minus of cos 2x by 4. And again, another integration which gives us minus sine 2x by 8. So now I multiply the first term under the d column with the second term under the I column, which is x square into sine 2x divided by 2. And now since we have a minus sign here and also a minus sign here, so that becomes plus. So we have plus 2x into cos 2x by 4 followed by minus 2 sine 2x by 8. So this is our integration, and like you can see, this is a very simple method where you just cannot go wrong. So I hope this made integration easier for you. However, there is one case where you cannot follow this method directly, which is called the recurring type. So let's say, for example, we have e to the power x into cos x. So here what happens is cos x being a trigonometric function gets the higher preference and it's taken as u, while e to the power x is taken as v. So we go on differentiating cos x. But like you can see, you're never going to get 0 here because differentiation of cos will give you minus sign, differentiation of minus sign will give you minus cos, differentiating it again will give you sine, and so on. So you're never going to get 0 here. So in this case, what we do is the initial few steps are simple, are the same, but we don't go on differentiating till we get 0. We just go on differentiating till we get the same term again. The sign can be different and there can be some other coefficients which are being multiplied with it, but you just have to get some form of the same term. Even if you had x cos x or cos x by x, it doesn't matter. You just have to get to the same term again. So I mean, not x, of course, because that is the variable we're looking at. Let's say we have k cos x or cos x by k. We just have to stop when we reach this particular term. And then what we do is we start in the same way again. We add a plus minus plus here. First term of t with second term of I, second term of t with third term of I. And then what we do is we multiply the last term here with the last term in the d column. So what we are getting is, let's say I, where my, let's say my e to the power x into cos x is I. So I have I is equal to cos x into e to the power x. Minus and minus becomes plus. So plus sin x into e to the power x. And now I have minus cos x into e to the power x. So like you can see, cos x into e to the power x is basically I. So I can write this as 2i is equal to cos x into e to the power x plus sin x into e to the power x. So since this is the value of 2i, I can simply write I as cos e to the power x into cos x plus sin x divided by 2. So in case you have a recurring type of integral, this is what is supposed to be done to get the final answer. So I hope that was clear. So now let us start with the actual topic. So the first question here is, what is a signal actually? So a signal is just a mathematical function. Like it can be any function. The simplest of function to t is equal to 1 to a complex function like sine t or cos t. So this is a mathematical function that conveys any sort of information. So any information that is being sent from one place to another is always conveyed in the form of a mathematical function, which we call a signal. And a system is basically an interconnection of physical quantities that performs certain operations on an input signal and gives us the output signal as we desire. Now, what operation the system performs on the signal, that is dependent on how we model the system and how I mean, it depends on what type of output we desire. So now, there are two types of signals, which are continuous and discrete. So a continuous signal is basically a signal that varies with time at every single instant of t. So let's say you have a graph like a very simple linear graph or a sine graph, or let's just any graph which exists at every single point t. Now let's say I'm trying to see the value of this graph at t is equal to 0.5. You can see that there still exists a corresponding value on the y-axis. So if you can find a value for every single instant of t, that means it's a continuous time graph. On the other hand, discrete time signals are defined only for integral values. So a discrete graph would look something like this. So this is 0, 1, 2, and 3. These are defined only at integral points. So now if I try to find the value of my function at t is equal to 0.5, it simply does not exist. And it works the same way for any other decimal values. These signals are defined only at integral values n. So that is the difference between continuous and discrete time. So what a system does is, systems are different based on whether the signal is continuous time or discrete time. So let's say we have a continuous time system that only takes in a continuous time input and only gives in a continuous time output. And similarly, if you have a discrete time input, it's entered into a discrete time system and we get a discrete time output. So the input is usually denoted by x of t, which is a function, and the system performs a particular operation on this and gives us a completely different function, which is y of t. And this is denoted by y of t is equal to t of x of t. This t curly bracket x of t indicates the operation performed by the system on this particular function. And for discrete time systems, we use n, which denotes the integral values. So we denote that as y of n is equal to t of x of n. So now we'll start with signal representation. Like I said, signals are basically just mathematical functions. So like functions are written in both uh, mathematical form as well as graphical form. So it's very important that we know how to draw the graph for a given function as well as we know how to write the mathematical expression for a given graph. So let's take this particular example where x of t is basically a straight line from -0 to 0 and then another straight line with a downward slope from 0 to 1. So how do we define this particular function in mathematical terms? Like you can see, this is not one function really. This is two functions. The function behaves differently from on the left hand side. It's increasing from -1 to 0, and then it's decreasing from 0 to 1. So this function is piecewise defined, which means it behaves differently in a particular region and differently in another region. So we can see that we can clearly define two regions here. The first one is the left hand side of your y-axis. So let's start with that region. Like the mathematical representation for a line is y is equal to mx plus c, where m is the slope of your line. So here what we do is to find out the actual function of this graph, we take the points which we already know for y and x. And since we know two different points for y and x, we'll get two equations of y is equal to mx plus c. And using those two equations, we can find the constants which are m and c. So let's substitute this particular value here. So we know that for y is equal to 0, x is equal to -1. So we have 0 is equal to minus m plus c. So I get m is equal to c. So this is my first equation. Excuse me. And the second equation is that at x is equal to 0, I get y is equal to 1. So I get c is equal to 1. And since I know that m is equal to c, I know that m is also 1. So substituting the values of m and c in our line equation, we get that y is equal to x plus 1. And here our x-axis is time and our y-axis is x of t, which is just to denote our input signal. So we know that x of t will be t plus 1. So now let's look at the other side of the graph. And a good way to check if you're actually getting the correct answer would be to just substitute the points and see if they're actually matching. And another thing that can be done to check is the slope. If the graph is going upwards, it clearly means you have a positive slope. So we just have to check if our slope is actually positive one. So like you can see, m is positive 1 here. So yeah, we didn't make any mistake. So on the other side, we have y is equal to mx plus c again. So here, for y is equal to 0, I have x is equal to 1. So that means m is equal to minus c. This is our first equation. And for the second equation, we have for y is equal to 1, I have x is equal to 0. So my c is equal to 1 again. This is my second equation. So I know c is equal to 1. and I also know m is equal to minus c. So that means m is equal to minus 1. So substituting y is equal to mx plus c, y is x of t, m is minus 1, and x is t plus 1. So this is my function on the right hand side of the graph. So like I said, this is a piecewise defined function. When t is between 0 and between minus 1 and 0, it's defined as t plus 1. And when the value of time is between 0 and 1, it's defined as minus t plus 1. So this is another question where there are four different regions where the function is piecewise defined. You can try this question on your own and to check the answer. I've uh, written the solution here. You can just pause the video, solve it on your own, and check it with the solution. The next topic that we'll be learning is addition, subtraction, and multiplication of signals. The division operator is simply not performed on signals, so we don't have to worry about that. So see, addition of signals is done in two ways. So the first case is where, let's say, the first signal is defined between 0 and 1, and the second signal is defined between 1 and 2. In this case, we can simply just overlap our signals uh, because from 0 to 1, the value of the second signal is simply 0. So that remains as it is. And for the first signal between 1 and 2, the value is 0. So that again remains as it is. So this is a simple overlap. Okay. Now let's take the slightly more complicated case where the first signal is also defined between 0 and 1, and the second signal is also defined between 0 and 1. In this case, what we do is we just learned how to represent a given function in terms of the mathematical expression. So we represent each of the signals in that way, and then we write our final mathematical expression, and then using that expression, we draw the graph. So the mathematical expression for this is simply 1, because regardless of what value of t you take, your x of t is going to come out to be 1. And the mathematical expression for this is x of t is equal to t. So I need to get a graph such that the resultant graph is clearly going to be the sum of these two functions, which is 1 plus t. So I need to draw the graph for 1 plus t. So if x of t is equal to 1 plus t, at t is equal to 0, my x of t is at 1. And for t is equal to 1, x of t is at 0. And so on. This is a linear graph again. So that is addition. And subtraction is almost the same thing, but like you can see, it's instead of adding things at a particular point, you will be subtracting the particular function and drawing the new function using what we just learned some time back. And multiplication again is the same thing, but what is different is let's say we are the functions that we added initially, if we are multiplying them, we'll simply get 0 because between 0 and 1, the second function is 0, and between 1 and 2, the first function is 0. So 0 into whatever the graph is, it doesn't matter because it's still 0 in every particular region. So when we are multiplying two signals, it's essential that there should be some common region where they exist, or else the entire product is going to come out to be 0. The next topic is amplitude scaling. So amplitude scaling is you have a graph between x of t and t. So what is the graph between 2x of t? So we keep all the points on t fixed. It's just every value on x of t is multiplied by 2. So let's say at 1 we have x of t is equal to 1. So now since we are multiplying it with 2, at 1 our amplitude goes to 2. And at 2, since we have 1, that 2 goes to 2. And at 3 we had the value of x of t as 2. And so we multiply that with 2 and the value of 3 becomes 4. So like you can see, the shape of the graph is retained. The only thing that has changed is the height or the magnitude. So this is amplitude scaling. Now if you amplitude scaled it at with a fraction, let's say you have half into x of t, then again the shape would be retained. The only difference would be that instead of it being a larger graph, it would have become smaller. The value at 1 would have been 0.5, at 2 it would be 0.5, and at 3 it would be 1. That would be the graph for x of t by 2. And if you're amplitude scaling it by a negative number, let's say you have by -1. So what you do is you just flip the graph around your x-axis, and that's how the graph for minus x of t will look like. So at 1 you'll have -1, at 2 you'll have -1, and at 3 we'll have -2. And similarly for -2 of x of t, it goes to -2 for 1, -2 for 2, and -4 for 3. So this is actually the better way to do subtraction between two signals. What you do is, if you have x of t minus y of t, you amplitude scale y of t by a factor of -1, and then simply add the two signals, because this can be written as x of t plus minus of y of t. So depending on what is actually convenient, amplitude scaling makes subtraction much easier. So all of this will be understood when we solve more problems. So though, if you are just able to understand the concept as of now, it's more than enough. Now we'll talk about independent variable transformations. We already spoke about amplitude transformations, but amplitude is a dependent quantity. Whatever is shown on the y-axis is a dependent quantity. So we spoke about amplitude scaling, which is transformation of a dependent quantity. Now we'll talk about transformations on the independent variable, which is time. So there are three different transformations that happen with time. The first thing is time shifting, the second one is time reversal, and the third one is time scaling. So time shifting is basically, if you have a particular graph, x of t and t, you just, like the word says, the graph is the same. It's just shifted to a different point on the x-axis. So this can be shifted either to the left or to the right. So if you have a function x of t and it's given to you, and if you are shifting it by a factor of minus t naught, then the graph shifts to the right. And if we are shifting it by a factor of plus t naught, it shifts to the left. So for an example, let's say this is x of t. So x of t plus 1, we just shift this graph by 1 unit. So whatever was at 0 will be at -1 now. And then the graph remains the same. There is no difference. The shape of the graph remains the same. It has just been shifted to the left by 1 unit. Now if you have x of t minus 1. So here what happens? It is shifted to the right. So the graph starts at 1, 0, and then the graph remains the same. The shape of the graph remains the same. The second operation that we'll be performing is time reversal, which is x of minus t. So here what happens is the graph is flipped about the y-axis. So whatever value was at 1, whatever was the value of amplitude at 1, it shifted to -1. And whatever was at -1 is shifted to 1. Whatever was at 2 will be shifted to -2 and vice versa, so on. So let's have a look at these two examples. So we just flip this about the y-axis. Whatever was at 1 goes to -1. And this is our uh, time reversed graph. And in this case, again, whatever was on the positive side goes to the negative side, and this is flipped about the x-axis. I mean, about the y-axis alone. The only thing that is always constant in time reversal is the value at 0. Everything from the positive side goes to the negative side, and everything from the negative side comes to the positive side, but the value at 0 remains fixed. The last thing that we'll talk about is time scaling. So what happens here is the graph is either compressed or expanded based on our scaling factor. So we have x of t, and that is transformed into x of at. So if a is greater than 1, my function is compressed. And if a is between 0 and 1, then it's expanded. So let's say I have a function x of t. Now, if I am time scaling it by a factor of 2, that is, I have x of 2t, whatever was the value at 3, that is shifted to 3 by 2. 3 by 2 less here. And whatever was the value at 2 is shifted to 1. Whatever was at 1 will be shifted to 0.5. So uh, the value of the amplitude at 1 is 1. So at 0.5 we have 1, and after that it just increases to 2. So at 0.5 is where this increase happens, and then it remains constant till, in this original graph, it remained constant till 2. But since we have compressed the graph by a factor of 2, now it remains constant till 1 before falling back, and then stays at 1 till 3 by 2. So the amplitude lies between 1 and 2. What we have compressed is the value on x-axis, which is time. So whatever was at 1 went to 0.5, and whatever was at 2 went to 1, whatever was at 3 went to 3 by 2. So now, if we are scaling it by a fractional number, what happens is whatever was at 1, that goes to 2. Whatever was at 2 goes to 4. And whatever was at 3 goes to 6. So here, our graph is going to expand. So at 1 we had the value as 1. So at 2 we have 1, and then the increase stays constant. And at 2 it comes back to 1. So here it comes back to 1 at 4. So this is time scaling. So if we have 2 into x of t, this is amplitude scaling, where the time is fixed, but the amplitude changes depending on our factor. And if we have x of 2t, here we are changing time, where amplitude is fixed. Like you can see here, amplitude is between 1 and 2 in all the cases. But what is changing is the time at which we are getting that particular amplitude. In case of amplitude scaling, our time remains fixed. What changes is the amplitude that we are getting at that particular time. So in both the cases, the shape of the graph remains same. In this, it's compressing and expanding, and in that, the height decreases and increases. I mean, in amplitude scaling, the height increases and decreases, and in time scaling, the graph compresses and expands. So one thing about time scaling is that when we have a discrete time signal, which is when the signal is only defined at non-integral values, what happens is some of the signals are lost, because let's say I have this graph x of n, and I'm time scaling it by a factor of 2. So what happens? Whatever was at 2 comes to 1. So at 1 we have the value 3, and whatever was at 1 should go to 0.5. So ideally at 0.5 we should have a signal which is 2. But the thing is, Like I said at the start, discrete time signals are only defined at integral values. So at 0.5, you simply do not have any signal. So because of this, there are few samples which get lost. Okay, so now we'll look at how these operations are actually used to solve questions. So obviously they're not going to give you a question with only one operation. You will be given a particular function x of t, and there will be multiple operations which are performed on that particular signal. There will be amplitude scaling, time shifting, and time reversal. So what we'll actually be looking at is the preference order that should actually be followed in case of multiple operations being performed on a signal. Let's say I have x of t and that has been transformed into a into t of minus not t of, this should be x of. So a into x of minus at minus b. So like you can see, this is amplitude scaling. You have time scaling, you are multiplying t by a factor of a. You have time shifting, it is shifting to the right by b units, and you also have time reversal because you have a negative sign with t. So it's very essential that you perform the operations in the given order one by one. So what we do is, the first thing that we do is time shifting. So we time shift x of t to x of t minus b. And then the next thing we do is time scaling. So x of t minus b becomes x of at minus b. And then the last thing we do is time reversal. So now we get x of minus a t minus b. And then at the end you can do amplitude scaling. The thing about amplitude scaling is it can be done at any point. That really doesn't make a difference. But the order between time shifting, time scaling, and time reversal should be followed very strictly, because if you scale it first and then shift it and then perform reversal, it gives you a completely different graph, which is the wrong graph. So it's essential that this order is always followed. So this is how multiple operations are performed on a particular signal. So this will be very clear once we do a few questions. But before we do questions, these questions actually involve the knowledge of a few important signals. So I'll just brief you about these signals, and then we can solve a few questions which will make sure you understand everything. So the first function that is important for us is the unit step function. So a unit step function is u of t is equal to 1 for any t which is greater than or equal to 0, and it's 0 at all other points. So the graph looks something like this. So till t is equal to 0, there is nothing in the graph, it's 0. And from t is equal to 0 onwards, the graph is 1. And then this goes on till infinity. So this is a unit step function. Now let's say I have u of t minus 3. What will my graph be? So since what am I actually doing here is I am performing time shifting, and it's shifting by a magnitude of 3 units to the right. Since it's t minus t naught, I'm shifting it to the right. So what happens here is it shifted to the right, and from here on it's 1 all the way till infinity. So this is the basic of unit step function. The next type of function is unit impulse function. So this is just defined at t is equal to 0. At this point you have value 1, and it's simply 0 at all other points. So this is defined as delta of t is equal to 1 at t is equal to 0, and at every other point it's it's 0, and at t is equal to 0 it's 1. So now if I have delta of t minus 1, it's the same thing that will happen. My graph just gets shifted by a unit of 1 to the right. So at t is equal to 1, I have the value 1. So that is what unit impulse function is. So we have a few formulae that are essential for unit impulse function. So the first one is L of n is equal to u of n minus u of n minus 1 x of n del of n is equal to x of 0 into del of n. Okay, I'm sorry for the delay. I did not prepare the PPT for this beforehand, so I had to write it down right now. So these are the important formulae that you just need to remember. These are the properties of unit impulse function. There are they there are chances of a very simple question using these functions which can be solved instantly, because these functions are very simple functions. They are just defined at a particular region and they have the same value throughout that region. So the last type of function that we'll be learning about is the unit ramp signal. So here what happens is x of t is equal to t at t is greater than equal to 0, and it's 0 at t is lesser than 0. So this is how the graph for unit ramp function looks like. And another important formula is differentiation of unit ramp signal. Let's denote it by r. R by dt gives us unit step function, and differentiation of unit step function gives us unit impulse function. So I hope that was clear. Those are the three important functions that we need to know. So now that we know about these signals, let's test how well we've learned the three important signals as well as the addition, multiplication, and the other operations that are performed on signals. Just give me a minute. Okay, so continuing with this. So let's say our first question is x of t minus no 2 minus t by 3, and the graph for x of t in this case is So this is -1, this is 1, this is 2, this is 1, this is 2, this is 3. Okay, so this is our this is the graph that we have to perform the given operations on. So like you can see, all the three independent variable transformations have been performed on this. So this is x of t and this is t. So the first thing that we need to do is time shifting. And this has been time shifted by 2 units. And since it's +2, we shifted 2 units towards the left. So my first operation will be time shifting. So I shift this graph 2 units towards the left. So it starts from -3 and it's upward slope till for 1 unit. So from -3 to -2, it's a upward slope, and then it remains constant for 1 unit. So from -2 to -1, I have a constant slope, and after that, uh, it goes up by 1 unit and stays constant for another unit. So from -1 to 0, again I have a constant graph. And then what happens is it goes down all the way to -1, and then there is a downward slope for 1 unit. So at 0 it goes to -1, and for 1 unit there is a downward slope. So it stops at 1. So this is 1, this is 2. So this is the graph for x is equal to t plus 2. So now we have done 1/3 of the question successfully, which is time shifting. So the next operation that we should do is time scaling. So just I hope all of you have drawn this graph because I will be going to the next page. So let's say I have why is this? Okay, I will have to add more slides. I'm very sorry for the disturbance here. I'm trying to get this done as fast as I can. Okay, let me just make as many slides as I can so that you don't face this issue again. Yeah, that's it. Okay, I am very sorry for that. Now continuing with this question, we have performed time shifting already. So the next operation as per the order is time scaling. So we have x of t plus 2 already. So now what we need to do is we need to scale this by a factor of 1 by 3. So let's draw the graph here. Okay, so if we are scaling it by a factor of 1 by 3, which is between 0 and 1. So what we basically will be doing is we are going to expand the graph. So if so, this was the graph of x of t plus 2. So for x of t by 3 plus 2, whatever is the value at minus 1 goes to minus 3, minus 2 goes to minus 6, and minus 3 goes to minus 9. The amplitudes do not change, they still lie between 2 and minus 1, and this whatever was at 1 goes to 3. Because of this, you get an expanded graph, which is let's have a look at this. So what the in the original graph, the value remained at 2 from minus 1 to 0. But since it's been expanded by a factor of 3 or scaled by a factor 1 by 3, we'll this is from minus 3. This is 1, and let's take this. So this is the value remains at 2 from 0 to minus 3. Then you have minus 4, minus 5, minus 6, minus 7, minus 8, and minus 9. Okay, and at 3, the value drops down to 1. In the initial graph, the value dropped at 1, but since you scaled it by 3, this particular drop in the graph happens at minus 3. And there it continued till t is equal to minus 2. But since it's been changed by a factor of 1 by 3, this graph stays the same till minus 6. And then we have a downward slope till minus 9. And on this side, at 0, the graph remains the same. From minus 1, this is 1, 2. So we have a downward slope from minus 1 to 3. So this is the graph of x of t by 3 plus 2. So that is 2/3 of the question done. So we have performed time shifting and we have performed time scaling. So the last operation that is left is time reversal. So now we have to find x of minus t by 3 plus 2. So this is, you just have to flip the graph about y-axis. So let's draw the graph here. So whatever was between 0 and minus 3 in that case comes between 0 and 3 here. So between 0 and 3 my value will be 2, and between 3 and 6 my value is 1, and from 6 to 9 I have a downward graph, and here I'm sorry for the terrible diagram. So from minus 1, minus 1, minus 2, and minus 3. So this is how my final graph looks like. X of minus t by 3 plus 2 t. So the first thing that we did was we time shifted it. We moved it towards the left by 2 units, and then we time scaled it. Since it was a fractional value which was lesser than 1, we expanded the graph. Whatever was at 1 went to 3, whatever was at 2 went to 6, and the shape of the graph remained the same while getting expanded. And then we finally performed time reversal. We just flipped our graph about the y-axis. So whatever was in the negative side came to the same positive side. So this is the first question. And for the second question involves both performing operations on a particular signal as well as addition of signals. And it requires knowledge of the unit step function. So let's let's solve the second one. This is given by x of t is equal to minus u of t plus 3 plus 2u of t plus 1 minus 2u of t minus 1 plus u into t minus 2 t minus 3. Okay, so we have four different signals here which we're supposed to add. So for actually adding each of these signals, we need to know what these signals actually look like. So let's plot all of them. So let's say my u of t is a very simple signal. From 0 till infinity, the value remains at 1. So now, if I'm finding u of t plus 3, what happens at t plus 3 is, for t plus t naught, my graph shifts to the left. So from minus 3 onwards, the value of this graph remains 1. And but I don't need u of t plus 3. I need minus u of t plus 3. So what is happening here is, if the minus sign was inside, it would be time reversal. But since the negative sign is outside, that means it's amplitude scaling. Anything that has to do with uh, being outside the bracket is related to amplitude scaling. So amplitude scaling of minus 1 is just flipping the graph about your x-axis. So this is my graph, minus u plus 3. So this is minus 3 and this is minus 1. So this is the first graph that we need. So now let's solve the second graph. Here it's t plus 1. So the first thing that we do is, it's shifted by 1 unit towards the left, and it's the same unit step function. It's all the way to infinity. Now the second thing that I need to do is, its amplitude scaled by a factor of 2. So so what happens in amplitude scaling is, the values of time remain the same. It's just the height increases by a factor of 2. So at whatever point the entire graph is at 1. So the entire graph gets increased by a factor of 2. So the entire graph becomes 2. So from 1, we have this is 2 all the way to infinity. So this is my second graph. So the third one is minus 2u of t minus 1. Like I mentioned at the start, the easiest way to perform subtraction between two signals is just perform amplitude scaling by a factor of minus 1, which is basically flip your graph about your x-axis and then add the signals. So what happens here is, the first thing that we need to do again is shifting it. Now since it's t minus t naught, the graph gets shifted to the right. So here we have from t is equal to 1 all the way to infinity. This is 1. So next I need to scale it by minus 2. So I reverse the graph, and this is 1. Since it's been scaled by minus 2, the graph goes all the way down to minus 2, and then after this point the value remains the same. So basically we have scaled it by a factor of minus 1 first, that is we flipped it, and then we scaled it by a factor of 2 again. That is, we multiplied the amplitude by 2 again. So this is the third graph, and then the last graph that I have is u of t minus 3. So this graph is again very simple. We just have to perform one operation, which is time shifting. And since it's t minus of t naught, it shifts to the right. So from t is equal to 3 onwards, the value of this graph remains at infinity. So now I have all four graphs, right? So now what I need to do is I need to add each of them. So like you can see, all of the graphs are just defined between uh, minus 3 and 3. After that, all of them have almost fixed values. So let's start from that. So what we'll be doing is, let's define each region minus 3 to minus 2, minus 2 to minus 1, minus 1 to 0, 0 to 1, 1 to 2, and 2 to 3. Okay, so now that we have performed all of these operations, we check what the value of each individual signal is in each of these regions, and we add all of them. And after finding all of this, we just plot the graph. So between minus 3 and minus 2, the value of this signal is minus 1. This signal is 0. This signal is again 0. And this signal is again 0. So between between minus 3 and minus 2, I have minus 1 plus 0 plus 0 plus 0. So my overall sum is just minus 1. So next, let me check for the next region, which is minus 2 and minus 1. So between minus 2 and minus 1, the value of this is again minus 1. The value of this is again 0 because it's starting from minus 1. The value of this is 0, 2, and this is 0. So it's again the same thing, minus 1. Now for the third domain, which is minus 1 onwards, like you can see, the value at minus 1 for the first graph is still minus 1. But now even the second graph has gotten a certain value, which is 2. The third ones and the third and fourth ones are still not defined, so they still remain 0. So we have minus 1 plus 2 is equal to 1. Now from 0 to 1, this is again minus 1. This is again 2 in the range 0 to 1. Uh, this graph is again 0, and so is this graph. So we have the same thing again, minus 1 plus 2 is equal to 1. So next, for the next domain, which is minus 1, no, the next domain is 1 to 2. This still remains minus 1. This still remains 2. However, now we have a third one. This from 1 to 2. The value of this is minus 2. And this is still 0. So we don't have to take this into consideration. So from 1 to 2, I have minus 1 plus 2 and minus 2. So this gives me minus 1. And from 2 to 3, I again have minus 1, 2, minus 2, and 0. So this is again the same thing, minus 2 plus 2 minus 2 is equal to minus 1. So for t greater than 3, the first graph gives me For t greater than 3, the first graph gives me -1, the second one gives me 2, the third one gives me -2, and the last one gives me 1. Because, see, there was no amplitude scaling in this, there was just time shifting, so the amplitude remains 1. So here, what I have is -1 plus 2 minus 2 plus 1. This is 0. So now that I have, and for t which is lesser than -3, my graph remains 0 because every single graph has a value of 0 below t is less t is equal to -3. So now if I plot my graph, I have to plot the value for each domain, I mean for each region. So let's plot all the points. -1, -2, -3, 1, 1, 2, and 3. So between -3 and -1, I had the value as -1, and between -1 and 1, I had the value at 1, and then again from 1 to 3, the value was -1, and after this, the value remains 0. All the way to infinity, it remains 0, and similarly, below this, all the way to infinity, it remains 0. So this is the resultant graph that we're going to get upon performing all of these operations. So I hope that made all of these concepts clear. I hope the concepts of addition, subtraction, amplitude scaling, time reversal, time shifting, and time scaling. I hope every operation is clear and what order should be followed while performing multiple operations. I hope that is clear to you. So the next thing that we'll be talking about is the different classifications of signals that exist. So signals are classified in three different ways. So the first thing is even or odd. The second type of classification is periodic and aperiodic. And the third one is energy and power. So let's talk about these one by one. The first one is even and odd. So an even signal is a signal where x of t is equal to x of minus t. So basically an even signal is symmetrical about y-axis. So here what happens is, like you can see, even if you perform time reversal, the function does not change. What happens in time reversal is everything on the positive side goes to the negative side and everything on the negative side comes to the positive side. But if your graph was symmetrical about the y-axis, that is everything on the positive side and the negative side were exactly the same, there is no difference when you flip things around. So that is called an even function. And an odd function is a function where x of minus t is equal to minus x of t. The only thing is, an odd function is always 0 at the origin. So the important concept here on the basis of which questions are actually formed is the fact that any function that you take can be expressed as the sum of an even function and an odd function. So what we need to know is how we can actually do this. So let's say the x of t is equal to xc of t plus xo of t. This is my first equation. Now if I take x of minus t, what do I get? X, if it's an even function, the even part still remains, but the odd part becomes minus xo of t. So this is the second equation. So upon solving these two equations, what I get is x e of t is equal to x of t plus x of minus t divided by 2, and xo of t is equal to x of t minus x of minus t divided by 2. So basically what we're doing here is we'll be given the graph of x of t and we have to find the even and odd parts. So what we do is we take the graph, we scale it by a factor of minus 2, we take a reversal of the graph, we scale that 2 by minus 2, and then we add it. Here similarly, instead of scaling this part, the time reversed graph by a factor of 1 by 2, we scale it by a factor of minus 1 by 2. So let's see how this is done using a question. So let's say I have this particular graph, x of t, and on the x-axis it's t, so 0, 1, and 2. So this is 1. Okay, so this is the function that we're given, and we're expected to find the odd part of this function and the even part of this function. So the first thing that like I said, we should do is we should find x of t by 2. So if we are amplitude scaling, what happens here? The values on x-axis, which is t, they remain constant. The amplitude gets reduced by a factor of 2. So we get 1 by 2. This is 1 and this is 2. So this is my x of t by 2. So now let's also find x of minus t by 2. So in time reversal, what happens? We flip the graph about the y-axis. So this is my x of minus t. So now to find x of minus t by 2, we just amplitude scale it here, and we get x of minus t by 2. So this is half, this is minus 1, and this is minus 2. So to find even part, what we do? What do we need to do? We need to find x of t by 2 plus x of minus t by 2. So these are the two graphs that we need to add. So like you can see, there is no coinciding region between the graph. This is defined between intervals minus 2 and 0, and this is defined between intervals 0 and 2. So this is the simplest type of addition. We just need to overlap both of them, and this is the graph that we get. This is minus 2, this is minus 1, this is 1, and this is 2. This point is 0.5. Okay, so this is the even part of the graph. So now to plot the odd part, what I have to do is I actually have to find minus x of minus t by 2. So the particular graph that I found here of x of minus t by 2, that has to be flipped about the x-axis. So This is -2, this is -1, and this is minus 0.5. Okay, so now what do I need to add this particular graph with the original graph of x of t divided by 2. So again, like you can see, there is no common region between the two. So the addition is pretty simple. You just have to overlap both of them. This is minus 0.5 and this is plus 0.5. 1, 2, -1 and -2. So this is the odd part of that particular function. So this is how you find even and odd parts of a given function. So the function can be expressed as a sum of this of these even and odd functions. All right. So the next type of function that we'll be looking at is periodic and aperiodic. So a periodic function is a function which repeats the same pattern after a given period of time. So let's say, for example, if I have a sine graph after a particular point, which is 2 pi, it starts to repeat itself. So that is called a periodic curve because and this is called the time period of that particular graph. Aperiodic signals are sort of random signals which do not really have a pattern repeating over and over again. So what we need to learn in this is how to find the time period of a given signal. So it's very essential that you know the trigonometric formula here because when they have given when they give a particular trigonometric expression, it needs to be simplified using those formulae before you try and find the period of it. So and another important formula that you need to know is e to the power j theta is equal to cos theta plus j sin theta. So this is another formula that has to be kept in mind because for any exponential question, if they ask us to find periodicity, it cannot be done without these formulas due to the complex number that is present. So now how do we find periodicity is the question. Let's say you have x of t is equal to e to the power j 3 pi into t. So what does periodicity mean? That after a particular time period, uh, let me represent this with small t. So let's say after a particular uh, time t, after this particular time t, the function tends to repeat itself. That is, whether you write t or whether you write t plus t, the function comes out to be the same, right? So when I write x of t is equal to e to the power j into 3 pi into t plus t, this term and this term should exactly be the same. So for that to happen, what should the condition be? Let's multiply 3 pi into the bracket. So I get e to the power j 3 pi into small t into e to the power j 3 pi capital T. So for this value to be equal to this value, the second half of this equation, which is e to the power j 3 pi into capital T, this should be equal to 1. Right? So e to the power j 3 pi t is equal to 1. So like I said, e to the power j theta is cos theta plus j sin theta. So let me write this as cos of uh, what is the exponent here? So I need to get cos theta plus j sin theta is equal to 1. So for this to happen, since there is no complex part on the right hand side, the complex part over here needs to be 0. So sine theta should be 0 and uh, cos theta should be 1. And this is achieved when theta is equal to 2 pi, right? So basically I need to get e to the power j into 2 pi for the entire term to be equal to 1, right? And what do I have here? 3 pi into t is equal to 2 pi. So pi gets cancelled and my t comes out to be 2 by 3. So this is the time period of this particular function. So let me just go through that again. What we did is we actually expressed e to the power j 3t in the trigonometric form, which is cos theta plus j sin theta. We just found out what the power of j should actually be for it to be 1, and we came up with the conclusion that only e to the power j 2 pi will give us 1, right? So e to the power j 2 pi is what will give us 1, and we know that e to the power j 3 pi into t is giving us 1, which means that 3 pi into t is equal to 2 pi, and upon simplifying we get that t is equal to 2 by 3. And another important thing is time period should always be a non-zero value, because t cannot be 0. That is like saying it's repeating after every 0th instant. For t is equal to 0, the function will remain the same at that point because you are checking it again at that point. So time period has to always be the smallest non-zero value that is possible. So there are a few more things about periodic functions that are essential. So if you have a trigonometric function, let's say a sine of omega t plus phi, and they're asking you to find the periodicity. So the function does not depend on a or phi. The only thing that the periodicity depends on is omega. So the rest of the function is literally irrelevant here. So regardless of what value of a you have and what value of phi you have, it doesn't matter. When you have a cos or sine value, the only thing that you need to look at is the coefficient of t. That coefficient of t is omega or angular frequency. So omega is angular frequency, and that is the only thing that matters. So let's see how we can find the periodicity of a trigonometric function. So let's say we have 2 cos of 3t plus pi by 4. So now what was the condition for periodicity? Upon replacing t with t plus t, I should get the original equation back. So let's replace that. 2 cos of 3 into t plus t plus pi by 4. So I get 2 cos of 3t plus pi by 4 plus 3 into capital T. So what we do is we take the initial part as A and the next part as B. So like I said, we have to keep our trigonometric identities in mind. So we have cos A plus cos of A plus B. So that can be written as cos A cos B minus sin A sin B. So this 2 remains the same, and I have cos of 3t plus pi by 4 into cos of 3t minus sin of 3t plus pi by 4 into sin of 3t. Okay, so now this expression that I just got should be equal to this original expression, right? So this is the original expression that we have. So for that to happen, the part that I'm multiplying it with should come out to be 1, and the part I'm adding or subtracting should come out to be 0. So here, what I need is I need sine of something to be 0 and cos of the same value to be 1. So like we already discussed, that happens only for 2 pi. So for cos of 3, if my cos of 3t is coming out to be 1, that means 3t is equal to 2 pi and t is equal to 2 pi by 3. So if you are approaching it with the logic of periodicity, then this is the way to solve the question. However, for trigonometric questions, there is a much easier way, which is by using the concept that I said, which is based on angular frequency. So we know that our periodicity does not depend on this 2 or this pi by 4. It just depends on angular frequency, which is 3. So we know that omega is equal to 3 in this case. So we know that omega is equal to 2 pi into f, right? So f becomes 3 by 2 pi. And we also know that time period is equal to 1 by frequency. So my time period is 2 pi divided by 3. So which is exactly what we got here. So with this, this is just the simplest way to find the time period of a trigonometric function. But again, if you have a subjective paper and the question has come for 5 or 10 marks, then this is not the method you use. But in case they have given multiple functions and they're asking you to find the periodicity and it doesn't really carry much weightage, then yes, and you need to save time. In that case, this method works. And this method can also be used to check the answer that you get from this method. So that is about time period of trigonometric functions. The another thing that you need to check time period for is, let's say you're given a function which is a sum of various other functions, phi 1 of t plus phi 2 of t and phi. So all three of these are periodic functions. So and we are given the period of each of them as 1.08, 3.6, and 2.025. So to find the period of this function, let's take this as t1, this as t2, and this as t3. So the first step to finding if this is actually the first step to finding the period of this function is to check if it's actually periodic or not. So for that, what we do is we see t1 by t2 and t2 by t3. No, sorry, t1 by t3 itself. So upon dividing both of these and simplifying it to the simplest form, we need to see if we actually get rational numbers. And if we are getting rational numbers, that means yes, the period does exist. So both t1 by t2 and t1 by t3 need to come out as rational numbers. So here, let's say we have t1 and we have 1.08 divided by 3.6. This is clearly 3 by 10. And here we have 1.08 divided by 2.025. This is 36. So this comes out to be 8 by 15. So since 3 by 10 and 8 by 15 both are rational, we can say yes, the periodicity does exist. So now to find the actual period, what we need to do is we need to take all the time periods. Let me write it in the fractional form. 108 by 100. T2 is 36 by 10 and T3 is 2025 divided by 1000. Okay, so now what we need to just give me a second. There was this issue. Okay, all right, let's go. I I was worried that this got disconnected. Okay, sorry. Okay, anyway, so we need to find all the time periods and write them in the simplest form possible, which is 108 by 100. I mean, we haven't simplified them yet. We need to write all of them in fractional form. And then what we need to do is we need to write it in the simplest form possible. So uh, both of them are divisible by 4. This is 25 and this is 27. This is both of them are divisible by 2. So 18 by 5. Both of them are divisible by 25. So this is by 40 and this is 81. So we have the it's very important that they're simplified to the simplest form possible. And after we do that, what we do is we take LCM of all three numerators and HCF of all three denominators. So here the LCM of these three numbers comes out to be 162 and the HCF of these three numbers is 5. So 162 by 5 gives us 32.4. So this is the actual period of y of t. So now this is for when it's expressed as a sum of three functions. So if you have just two functions, you just need to find t1 by t2. If this is a rational number, you can say that it is definitely periodic. And then we need to write t1 in the simplest form, simplest fractional form, t2 in the simplest fractional form, and then again LCM of numerators, HCF of denominators. Regardless of how many terms you have, the process remains the same. Express each time period in simplest fractional form, find the LCM of all of the numerators, find the HCF of all of the denominators, and divide both of them. So that gives us the periodicity of a function. So that is that's it about periodicity. The next and the last classification of signals that we have is the energy and power signal. Energy power signal. So here we need to know the formulae. For continuous time, energy is given as integration of minus infinity to infinity mod of x of t square t, and power is given by limit of t tending to infinity 1 by t into integration of minus t by 2 to t by 2 mod of x t square. Okay, so now I know the logical question here in these formulae is that when we are squaring a particular term, we shouldn't have the need to apply modulus because I mean squaring makes it positive anyway. But the modulus exists here because in case we're talking about complex functions, the modulus is what actually helps us to write to actually find the energy or power because the modulus tells us that we are only going to be talking about the magnitude of the particular function. So that's why even though we have square, we ensure that the mod sign exists. And for discrete time signal, we have See, because the continuous time signal is a continuous graph, to sum up every single value, we have to integrate it. But since this is a discrete time graph where we have to add only particular values, we'll be using summation of n is equal to minus infinity x of n mod square. And the same thing with power, where limit of n tending to infinity 1 by n, and the summation here goes from, this is important, the summation goes from n is equal to 0 to n minus 1 mod of x of n whole square. So the type of questions that we get in this are, they give you a particular signal and ask you to check whether it's an energy signal or a power signal. So how we do that is basically, uh, first we check whether, since energy is actually defined from minus infinity to infinity, if the graph is actually not something which is bound in a particular region, right, the energy will actually come out as an undefined term, due to which we can say it's not an energy signal. Right? See, another thing that I forgot to mention is the power that we're talking about here is the average power. All right. So even if the signal is not defined, we know that the average power remains the same. So because of that, certain signals which do not have a defined energy end up having defined power. So these signals are called power signals. But if the energy itself is defined because the signal is bound in a particular region, then it's called an energy signal. Now, if we do not get a rational value of either energy or average power, then we can say that the signal is neither energy nor power. So the questions are always going to be about what type of signal the given signal is. So let's see a few examples here. So the first example is, let's take a discrete signal one is equal to minus 0.5 to the power n into u of n. So the first thing is, if whenever there is a question of a particular function with just multiplying it with u of n, the only thing that you need to really do is just remove all the negative values of that particular function. Anything on the left side of the y-axis is just not going to be considered anymore. So let's say this is minus 0.5 to the power 0 is, there's no difference here. So at 2, I have uh, just a minute. Oh, yes, yes, yes. So the thing is, what will the value of this function be at 1? Minus 0.5 to the power 1 ideally gives me minus 0.5. But since I'm multiplying it with unit step function, anything on the left hand side of the y-axis is considered useless. So, and it's not just for 1, for any odd powers of n, the value of this would have lied on the negative axis. But since we are multiplying it with unit step function, anything on the negative axis is not considered. So let's only consider even powers. So let's say minus 0.5 square. So that gives me 0.25 minus 0.5 to the power 4. That gives me 0.25. 0.0625 and so on. We don't need to calculate each of these. The only thing is, this is approximately how my graph looks like. So this is the value at -2, this is the value at -4, this is the value at -6, and so on. So the formula of energy is usually summation of n is equal to minus infinity to infinity. But here, since everything from minus infinity to 0 is 0, we don't have to consider that part. We just have to consider n is equal to 0 to infinity magnitude of x of n whole square. So this is basically a summation n is equal to 0, infinity 0.25 plus 0.0625 and so on. So like you can note, this goes on till infinity. So like you can notice, the difference here is the number is getting smaller, and it's getting smaller by a certain fraction each time. So what does this actually represent? This represents an infinite GP, an infinite geometric progression where the where my A is 0.25. A is the first term of the geometric progression, and R is again 0.25. As you can see, this is into 0.25, again into 0.25. That's what's going on. So we know that the formula for sum of infinite terms in a GP is given by A divided by 1 minus R, as long as your R is lesser than 1. So here we have A as 0.25 and R as 0.252. So that becomes 0.25 divided by 0.75 is 0.33. So since we got a rational value of energy, we can say this is an energy signal. Okay. So this is the see, if we get the signal as an energy signal, we don't have to go further. We can just confirm that it's an energy signal and leave it at that. Okay, so the next question is x of n is equal to 2 into e to the power j3n. Okay, so this is an extremely important concept because you have a complex number in here. So we always need to make sure we're taking the magnitude, right? So, and we also know that e to the power j theta is written as cos theta plus j sine theta, right? So we can write this as 2 into cos 3n plus j sine 3n. So now when we're talking about energy, what we actually do is 2 into summation of n is equal to minus infinity to infinity magnitude of e to the power j3n square. See, when we are actually doing performing what we are doing is performing a magnitude operation on cos of 3n plus j sine of 3n, and magnitude is just when you have a plus bj and you're a complex number and you're trying to find its magnitude, it's given by root under a square plus b square. Similarly, when you find the magnitude of this function, you get root under cos square 3n plus sine square 3n. And we know that cos square x plus sine square x is 1 and root of 1 is 1. So the important thing here is magnitude of e to the power j into anything will always give us 1 because cos square plus sine square, regardless of what is in the bracket, will always give us 1. So we can conclude that the magnitude part here is 1, but we have 2 infinite, n is equal to minus infinity to infinity of 1. So this just means we'll have 2 into 1 plus 1 plus 1 all the way till infinity. So this is not defined because you're just going on adding ones till infinity. So the value of that is infinite. So since it's not defined or a rational number, we can say this is not an energy signal. It's definitely not an energy signal. So we need to proceed and check whether it's a power signal. So for power signal, what the formula is limit of n tending to infinity 1 by n into summation of n is equal to 0 to n minus 1 uh, mod of x of n square. So see, we already saw that this part is 1. So we have 1 by n into summation of n is equal to 0 to n minus 1 ones. Right? This part remains here. If we are adding ones n minus 1 number of times, the sum, what does the sum come out to be? So let's see with a few examples. Let's say I'm adding it all the way up to 4. So so basically, if my n is 4, I will have to add ones till 3. So n plus 1 plus 1 plus 1. So this comes out to be uh, from 0 actually, because at the value of at the point n is equal to 0 2, I have 1. So this is at 0, this is at 1, this is at 2, and this is at 3. And the value has come out to be 4, which is what n actually is. So anytime you're performing summation of n is equal to 0 to n minus 1, 1, you can conclude that the value is going to be n. Okay, so because of that, we can write limit of n tending to infinity 1 by n into n. Here n and n get cancelled, so we just have 1. So since the power is actually a rational number, we can conclude that the whole thing is rational. I mean, the average power is rational, so this is a power signal. So that's how you check whether a given signal is energy or power. In case we do not get this as a rational number too, then we would have concluded saying it's neither energy nor power signal. So with that, we have come to an end to the classification of signals. Now we have orthogonality, mean square error, norms and moments. So we're done with about 75% of the chapter. We're done with most of the important stuff actually. So norms and moments are a very small part of it. It's not really a it's not really something which is significant for the from the exam point of view either. But yes, orthogonality and mean square error are quite important. So what does mean square error actually mean? Is uh, when you are representing one signal, let's say V1, in terms of another signal V2, and you're multiplying it with C12 to express it as the form of the other signal. So here what you're doing is you're expressing V1 in terms of V2. So this is a approximation because here you tend to get a small error. So what does this what is important here is the actual formula of C12, which is given by integration from T1 to T2 f1 of t into f2 of t divided by integration of t1 t1 to t2 f2 square t, and this is also dt. So here f1 is the function that you're actually what do you say, expressing, and f2 is the function in terms of which you're trying to express f1. Okay, so c12 is just uh, it's giving us the relation between f1 and f2, like by multiplying what number or what term into f2, you will actually get the function f1. So because this is a very good system to express it, but there will always be a certain error due to which we have this PE or the error vector mentioned separately. So let's just wrap this concept up with one question. So let's say we have a function f of t is equal to 1 for 0 to pi, and it's minus 1 for pi to 2 pi. So we need to find C12 and error function here such that for sine waveform. So basically what we are trying to do is we are trying to find the sine waveform in terms of the given function, right? So to give a more visual idea, let's say this particular graph is 1 from 0 to pi, and from pi to 2 pi it's minus 1, right? So the sine graph basically oscillates between these points. So like you can see, there are a few parts of the graph which are left out. So what we are trying to find out is how much are these parts actually, how large are these parts actually there? I mean, how large are the parts that are present here? So we are trying to find out C12. That is, this is a variable, or I should say, that actually relates this rectangular function with the sine waveform. So how do we do that? Is with the help of the given formula, that is the integration of t1 to t2 f1 of t into f2 of t divided by integration from t1 to t2 f2 square of t. Both of them are integrated with respect to dt. So here my f1 f1 of t is the given function, and f2 of t is sine t. So first let me try to find the differential the integration of the denominator. So I have 0 to 2 pi sine square t dt. So here what we do is we split sine square t using the trigonometric identity, which is 1 minus cos 2t divided by 2. So again, upon splitting it, we get half into integration of 0 to 2 pi 1 minus cos 2t dt. That gives me half into t minus sine 2t by 2 from 0 to 2 pi. So upon substituting these limits, I get half into 2 pi uh, and the sine terms all become 0 because sine of 2 pi gives me 0. So all I'm left with is pi. So the denominator of C12 is pi. Now to find the numerator, we know that the numerator is piecewise defined. So from 0 to pi, it's 1. So that is there. And from is from pi to 2 pi, we know it's minus 1. So we take a minus symbol here, followed by sine t dt. So now it's again simple integration. This gives us minus cos of t from 0 to pi. And this is this becomes cos of t from pi to 2 pi. Okay, so this gives us 4. So this 4 is the numerator and this pi is the denominator, right? So my C12 is 4 divided by pi. And if anyone asks the error function in this question, the error function is, what is the error function? The error function is when you have written f1t is equal to c12 into f2 of t plus error function, right? So for error function, we write it as f1 of t minus c12 into f2 of t is equal to fe. So in this case, we have f1 of t minus 4 by pi sine t. This is our error function here, right? So that is about mean square error. The next formula, the next another thing that I just forgot to add is in this case, if uh, if we are talking about complex numbers, let's say either of our functions were complex, we replace f2 by f2 conjugate, right? So what conjugate does is if you have a plus bj, it's changed to a minus bj. And here too we take the conjugate and then the modulus. So we have integration of t1 to t2 f1 of t into f2 conjugate t divided by uh, the integration is the same again t1 to t2 f2 conjugate. We take mod here f2 conjugate of t square. And again, the mod here denotes that it's simply magnitude alone, right? So that is a small change that takes place when we're talking about complex numbers. So the next topic is orthogonality and orthonormality. So here the questions are very direct that they will give you two curves or two signals and ask you to check whether they are orthogonal or orthonormal. So the condition for orthogonality is T1 integration of T1 to T2 f1 of t into f2 of t dt is equal to 0, right? And again here, if the functions are complex, then instead of f2 of t we write conjugate of f2 of t. And orthonormality is when the condition for orthonormality is that both uh, the integration of squares of both the function is equal to 1. f1 square t is equal to integration of t1 to t2 f2 square t is equal to 1. Both of them are with respect to t again. So this is the condition for orthonormality. So let's have a look at a question for orthogonality. See, like I said again, this is a very direct question. You just have to integrate two functions from a given limit. So, and then if it comes out to be 0, you can say that it's orthogonal. And if it's not 0, then it's not orthogonal. Just give me a second. Yes, so usually in orthogonality, the questions that they give are related to sine or cos or e to the power some function. So let's just have a look at one question where f1 of t is given as sine of n omega naught t, and f2 of t is given as sine m omega naught t, and n is not equal to m. Okay, so and it's given that the time period is from 0, 0 to t plus 2 pi by omega naught. No, it's actually from t naught to t naught plus 2 pi by omega naught. So to check orthogonality, what we do is we integrate it from t naught to t naught plus 2 pi by omega naught, and we have sine n omega naught t into sine m omega naught t. Okay. So this is of the form sine A into sine B, the identity for which we have as cos of A minus B minus cos of A plus B divided by 2. So upon substituting this identity, we get 1 by 2 integration of, uh, 1 by 2 integration of t0 to t0 plus 2 pi by omega naught. Here we have cos of n minus m omega naught t minus cos of n plus m omega naught t dt. Okay, so this is like a just normal integration now because cos of n minus m is integrated to give sine of n minus m omega naught t divided by n minus m into omega naught, and this gives minus cos of n plus m into not cos or sine into n plus m omega naught t divided by n plus m omega naught. So now upon substituting the values, substituting the limits t naught and t naught plus 2 pi by omega naught, what we get is this half remains common outside anyway, so we don't have to bother about that. We'll get sine of n minus m. Upon multiplying it with t naught, we get n minus m omega naught t naught divided by n minus m. Uh, this whole thing is inside sine n minus m omega naught, right? And this part, uh, okay. What we actually need to see here is when we are substituting t naught plus t pi by omega naught, right? So we get omega naught t naught plus, wait, let me just write this entire thing again. So yes, first what we do is we substitute the upper limit, and I get sine. Inside sine I have n minus m into omega naught. In place of t, I write t naught plus 2 pi by omega naught divided by uh, Here we have n minus m omega naught. So let me just simplify the first expression here a little further. This will give me sine of uh, sine of n minus m into omega naught t naught plus n minus m into 2 pi, right? So this is n minus m into omega naught. So what we can actually do here is this n minus m into 2 pi, it's neglected because the reason for this is because 2 pi is actually the time period of sine. So whenever you add any multiple of 2 pi to a given sine function, it remains the same. So we can just neglect this part and write it as sine of n minus m into omega naught t naught, right? And we can see that upon substituting the lower limit, you're going to get the same thing. You're going to get omega naught t naught. So upper limit minus lower limit comes out to be 0. And similarly for the second expression. So you know that finally it all gets cancelled. I'm not performing the calculations here. It's a very easy one because you just have to substitute the limit and you know that the 2 pi term gets neglected. You just have to proceed and you'll get all the first uh, terms upper and lower limits cancel each other out, and the second terms upper and lower limits cancel each other out. So that is about orthogonality as well. So now we are left with norms, moments, and linear dependency of vectors. Another thing is whenever I just want to add a short point that uh, cos, sine, and e to the power j anything, these are orthogonal for all integral values. And so yeah, so that's about orthogonality. Now we will talk about moments of a signal. So a moment is basically a measure of signal size based on area. That is the definition of moments, signal size based on area. Alright, so we have various moments. For example, let's say we have the nth moment. The nth moment is given by mn is equal to integration of minus from minus infinity to infinity t to the power n x of t dt. Alright, so depending on uh, what moment you are taking, you get a different signal size. You get something which gives us a measure of signal size, right? So let's say I'm taking m of 1. I get integration of minus infinity to infinity t to the power 1, which is just t x of t dt, right? So this m1 is called mean. It's called the mean of the given signal, right? So like I said, different moments give us different informations about the signal. So my m1 gives me mean. M2 would be minus infinity to infinity t square x of t dt, right? This gives me the mean square value of the given signal. So it's the you just need to remember all of these terms because the questions do not ask you for first moment and second moment. They ask you for what is the mean of the signal and what is the mean square value of the signal. Right. So the third thing I will look at is mx, which is m1 divided by m0. This is called the normalized first moment. So here you need to find m1 and m0. I think I forgot to mention m0. Yeah. m0 would be t to the power 0, which is just 1. That would be m0 would be integration of minus infinity to infinity x of t dt, right? So that is the normalized first moment. Uh, the normalized second moment is normalized second moment. This is not really significant, but anyway, normalized second moment would be m2 divided by m1. No, I'm sorry, m2 divided by m0. So whenever you normalize any single moment, you divide it by m0, right? So this is then let's denote this by mx, and this is there is no specific way to denote this, so let's just write it as m2 divided by m0. So why this is significant is whenever we are talking about AC power, it's given by m2 divided by mo minus mx square. So m2 by mo gives me my total power, and mx square gives the DC power, right? So this AC power is variance, which is denoted by sigma square. So sigma, which is standard deviation. So this is denoted by root under m2 by mo minus mx square. Right. So mx is used to denote delay in a signal, while sigma denotes duration or spread of a signal. Alright, so when if they what they do is they give you a particular function, and they ask you to find stuff like delay, duration, AC power, usually because the normalized first moment and second moment are very simple. So finding things like duration means that you have a few more calculations, but that's it. Apart from that, there is nothing in nothing in moments. Moments, norms, and dependency of vectors are very simple. They're just basic topics which we need to cover. So norm is again a norm is a measure of signal length. So again, norms like we had different moments m1, m2, and so on. We have norms to L1, L2, and so on. So L1 is just integration of x mod x t dt. L2 is uh, root under integration of mod x t square dt, and so on. If you are talking about discrete, we have L1 is equal to uh, just a second. Yeah, for discrete, we have L1 is equal to summation of x n, and for L2, we'll have summation of xn square root. That will be L2, and so on. The only thing that you have additional for norms is called L infinity, and this is given by mod of x of t infinity. So what this does is this just denotes the maximum value uh, in that particular signal length. So this is called peak absolute value. So let's just, for norms, let's have a look at a question. Let's say we have x of n is equal to 3, comma minus j4, comma, comma 3 plus 4j. So we have this, this is a discrete type signal where basically it's like at n is equal to 1 you have a particular value, at 2 you have a particular value, and at 3 you have a particular value. Alright, so let's, we have been asked to find x1, uh, x2, and x infinity. So the first thing that we need to do is for x1, it just becomes summation of mod of xn. So we need to take the modulus of each of these. So 3 remains 3. J minus j4 square becomes minus j4 square becomes 4, and 3 plus 4j in magnitude becomes root under 3 square plus 4 square, that is 5. So we get 12 here. And then for x2, we have to take, this is 1. So for 2, we have to take root under summation of xn square. So here we square each of these terms and find their overall root, right? So this becomes 9 plus 16 plus 25, and that gives us root 50. And the last thing we need to find is the peak absolute value. So we need to find the magnitude of each of them, right? For peak absolute value, what we do is we find the magnitude for each and every single given point, and the magnitudes are found to be 3, 4, 5. And we just choose the maximum value amongst these, right? And like you can see, the highest value here is 5. So that is the value, that is the answer for peak absolute value. Alright, so we are almost done here. The last topic is linear dependency of vectors. Right. So here what you have to do is to check whether two vectors are linearly dependent or not dependent. We can do, there are two different methods. The first one is expressing it in a form of a linear equation, and the second one is using the determinant. So I would suggest use the determinant for 2 cross 2 and 3 cross 3, but 4 cross 4 determinants again get complicated. So when it comes to that, expressing it as a linear function is what is actually going to help us. A linear function which is in its standard form, like ax plus by plus cz is equal to d. That in this form, expressing it is what will help us, right? So let's take an example for each. So like I said, if you have a 3 into 3 form, then use the determinant. So let's say we have x, which is 1 comma 6 comma 5, another vector y, 1 comma 1 comma 0, and another vector z, which is 7 comma 5 comma 2. What we need to find is we need to find the determinant of all of them. So we take all the x values in a row. I mean the x coordinate values of all 3 points, which is 1, 1, and 1. Then 6, 1, and 5, 5, 0, and 2. Right. So if the determinant of this comes out to be 0, if let's say this is mod a is equal to, so if mod a is equal to 0, then it is independent, and if it's not equal to 0, then we can say that it is dependent, right? So upon calculating this determinant, you will get it's equal to 4. So we can say that these are all linearly dependent vectors, right? So next we'll see for four different vectors. So let's say you have x minus 1, comma 0, comma 2, y, which is 2, comma 1, comma minus 1, z, 0, comma 2, comma 1. And let's take w, which is 1, comma minus 2, comma 1. So like I said, for this, let's uh, let's not take a determinant because 4 into 4 determinants get complicated. Let's take it of the form ax plus by plus cz is equal to w. Right. So which is a is minus 1, 0, 2, and b is 2, comma 1, comma minus 1, and c is 0, comma 2, comma 1, and that is giving us 1, comma minus 2, comma 1. Right. So we just need to add all the x-axis parts here and equate it to the x-axis part here. Right. So that gives us minus a plus 2b plus 0 is equal to 1. So that is one equation for me. So the second equation will be 0 into a, which is 0, plus b plus 2c is equal to minus 2. So this is the second equation. And then we need to see the third equation, which is 2a minus b plus c is equal to 1. Right. So I'm just looking at the x coordinates of each of them. Uh, the x coordinates on the left hand side should sum up to 1 because that is the x coordinate on the right hand side. So that's what we've been doing here. So now that I found three equations and I have three variables a, b, and c, I have to find the values of a, b, and c. If a is equal to b is equal to c is equal to 0, that means they are linearly independent. And if even one of them is not equal to 0, that makes them linearly dependent. Upon calculating, you'll find that none of A, B, or C are 0. That means this is these are all linearly dependent vectors. So I did not know the last two topics that we did are pretty minor topics. Actually, they're you don't really have to spend much time practicing additional problems for any of them. But for the initial few questions, I would say practice few questions, not initial few questions. I mean, the initial few topics, I would suggest that you practice a few questions for each topic because that helps you solve questions faster and it just reduces your chances of a mistake drastically. See, at one point, when you solve a few questions, the time shifting, time scaling, and such operations become so easy to you that you're not even going to require making the graph stepwise. You can look at the graph and immediately predict what the final output is going to be like. So, I mean, even though you still have to show the steps when it comes to subjective paper, what this does is it just gives you the guarantee that you have not gone wrong because you're going to look at the graph and you're going to know the output and then you're just going to write the steps for arriving to that output. So this is a completely mathematically based subject, and for any mathematical subject, it's obviously important that you practice more questions. I hope that every question on here was understood. And I would say for the last few topics, it's not really essential to practice more questions. But at least for the first few topics, up to let's say energy and power signals, it would be nice if you can practice more questions. I wouldn't say you will not be able to solve the questions in the exam because I made it such that I included every type of question here. But just for your own confidence and to be more fluent and not panic in the exam, I would say solve a few questions if possible from any teacher's notes, and that should be more than enough for your exam preparation. Two questions per type is more than enough. So, and if you really do not have any time because you're running short, it's all right. just don't panic in the exam because I can guarantee you that everything covered in this lecture is enough for the exam. So I hope you have understood, and I hope this lecture was helpful for this particular subject. I hope it developed an interest for you in this subject, and for sure, I hope it will get you the marks you want. So, thank you, and we'll meet in another lecture.